Okay, so we had been working on simplifying quadratic expressions. We had finished doing that last time. So we'd been talking about simplifying. Right, where we had working on kind of converting between the different forms of quadratics using this map, right? And we had talked about how to do all these different little operations on how to transform in between these forms. And it finished up last time doing like all the factoring shortcuts to kind of get you accustomed to some of the things that we can do to allow us to do the factoring quickly, right? So that was kind of tied up the end of simplifying. Today we're going to start solving. So the solving situation that we're going to look at first is with intercept form. And the key here, or the key tool we're going to use for solving something in intercept form is called the zero product property. That it says A times B equals 0 if and only if A equals 0 or B equals 0. So if you have two things that multiply together to give you 0, the only way that happens is that one or both of them is equal to 0, right? Hopefully that feels very common-sensey. But this is a very special property because 0 is the only number that this works for. Right? If you have two things that multiply to give you 1, there's infinitely many pairs of numbers that do that. You could have 1 and 1, you could have 1 and 1, or 2 and 1/2, 3 and 1/3, 4 and 1/4, etc., 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 not even counting the negatives, right? So then, say we have the intercept form row, like this one. If we want to solve this, we can apply the zero product property and set them equal to 0, and then solve them each as their own individual problem. So I can subtract 4 from both sides to get -4, and add 5 to both sides, +5, and those are my solutions. Is everybody okay with that idea? And just to FYI that this scales, that if you have like 10 things multiplied together that equal 0, you can take each of those 10 things, set each of them equal to 0, and solve for each of them independently. Okay? So the zero product property, it doesn't require just two things. You could have as many things as you want, as long as they're all multiplied together and it equals 0. You can use it quite flexibly. Okay, there? So for the most part, we don't encounter quadratics that are in intercept form that often. So let's talk about what we would do if we have a standard form polynomial. What we do is we can try to take our standard form polynomial, convert it to intercept form, and then try to use that zero product property then. So for example, let's say we have x squared plus 10x plus 16 equal to 0. That's a standard form polynomial, right? How can I convert it to intercept form? We factor it, right? So we need two numbers that multiply to give us 16 and add to give us 10. Those two numbers would be 8 and 2. So we can write this as x plus 2 equal to 0. Okay there? What's the problem with this though? As a method. Yeah, so remember that factoring doesn't always work. Absolutely correct. So that's not always going to be possible, right? So we'll have to come back and look at that in a minute to see if we can fill in a method to deal with those situations that maybe are not possible. So far, are we okay, though? So let's say we have a quadratic that's in vertex form. So for vertex form, use just the reverse order of operations to solve that quadratic directly. So let's look at an example. Actually, so let's say we have, oh my goodness, let's make this a 2 over here. Sorry. I just wanted to get this to have enough things happen to make it worth our while. Okay. So when we say order of operations, we're talking about Pemdas, right? When we simplify, we kind of go in that direction where we do parentheses, then exponent, then multiplication, division, and lastly we do addition, subtraction. When we solve, we go the opposite direction. So we're undoing things. So that means that we should be going in the opposite direction when we're solving, right? So the first thing I would want to do is undo any addition or subtraction. Well, I see one subtraction instance and one addition instance. However, the x plus 5, that plus 5 is inside of the parentheses. Do you guys see that? So to get access to the x plus 5, I'd have to clear the parentheses out first. So I'm not going to worry about that until I've done that. But I do have access to the minus 14. So I would just start by adding 14 to both sides. Okay, there. So the next thing I would look to undo is any multiplication or division. Well, I have a times 2, right? There's multiplication going on in between that 2 and the parenthesis that we usually write the multiplication symbol, but we know it's there. So to undo that, what do? I divide both sides by 2. Everybody okay there? Okay. Now we have to worry about any exponents. We have an exponent in this problem, right? We have this squared. How do I undo that squared? I square root both sides. So when we do that, let's make a little aside here, because there's some facts about square roots that we probably need to either see for the first time or at least refresh our memory on. So let's a little aside. So the first thing is that we need to make mention is that when we square root both sides of an equation, that creates a plus or minus. That if we have the square root of a product, that can become the product of the square roots. And similarly, the square root of a quotient can become the quotient. But that's not true for addition and subtractions. So the square root of a sum or a difference is not the sum or difference of the square roots, except in very trivial circumstances where like one of the a's or b's are 0 or something stupid like that. Everybody okay with that information? Okay. So we've seen plus 5 squared. The squared and square root cancel, so I have just an x plus 5. Because I did the square root of both sides, I have a plus or minus. And then I have the square root of 8. I don't want you to create decimals anytime we're dealing with one of these problems where we run into a square root. Unless I expressly tell you to round. I don't want you to round unless I tell you to. So just leave it as the square root of 8, because that can't turn into a whole number. But the square root of 8 can get more simple. Hopefully, when you look at the square root of 8, you recognize that the square root of 8 is the same thing as the square root of 4, or is the same, 8 is the same as 4 times 2, right? So the square root of 8 is the same as the square root of 4 times the square root of 2. Why would it be helpful to do that? Because we can find the square root of 4. So really let's call this plus or minus 2 root 2. Is everybody okay with that? Okay, but we're not done because we still have x plus 5, right? So we'll just subtract 5 from both sides. Now, can I combine with something that has a square root on it? No, those are not like terms, so we're just going to write it next to it. So there's our final answer. Is that okay? What about a situation like this? Is this still vertex form? Technically it is, right? Because we can think about it as 2 times x minus 0 squared. So it's still technically vertex form. Everybody's okay with that? It also could be considered standard form, right? But that's what we're trying to get back to, is filling in some of these standard form problems that we couldn't factor. Everybody's okay with this, though, that this is still could be considered vertex form or standard form? Since we can still consider it vertex form, we can solve this using the reverse order of operations. So I can add 9 to both. And then divide both sides by 2. And then we can square root both sides. So because we square rooted both sides, we get a plus or minus. And because we have the square root of a fraction, we can do the square root of 9 over the square root of 2. Everybody still feel okay? Now the square root of 9 we know how to do. That's just 3. But you guys should remember from your geometry class last year that we don't like to leave a fraction with a square root in the denominator, right? That happened on you guys when you were doing your sine, cosine, tangent stuff on a fairly regular basis. Do you remember what you did to get rid of that or to fix that problem? Well, it's an easy fix. We're just going to multiply the top and bottom of this fraction by some number that's going to get rid of the square root in the denominator. What might that number be? The square root of 2 in this case. The same square root that's in the denominator. And the square root of 2 times the square root of 2 is the square root of 4, or just 2. And there's our final answer. Everybody okay there? So regardless of how that vertex form problem is written, we can always solve it, right? That's going to unlock the key to being able to deal with the rest of our standard form polynomials. Because we can always take a standard form polynomial and rewrite it as vertex form by completing the square. And then we can solve using that reverse order of operation. OOP is order of operations. Oh, that's 3 O's. I don't know where my P was coming from. Everybody okay with that notion? So let's definitely not factorable. That's standard form. That can't be just trivially rewritten as vertex form. Like this one. 2 things that multiply to give me -5 and add to give me +2. No problem. Okay. So to complete the square, the first thing we want to do is make sure the leading coefficient is 1. Taken care of for us, right? There's no problem there. Then we're going to add and subtract b over 2 squared. So in our case, b divided by 2 squared is 2 divided by 2, which is just 1, and 1 squared is 1. So we're just going to add and then subtract 1. Now x squared plus 2x plus 1, that factors, right? What does that factor to? Okay, but we're going to write as x plus 1 squared, like that. And then -1 and -5 is just -6. And now it's in vertex form, right? So we could now solve this directly. To both sides, square root both sides. Doing so makes a plus or minus. And the square root of 6 can't be simplified anymore, right? Because 6 is just 2 times 3. So can't do anything. Back the 1 over. So it's just going to be -1 plus or minus the square root of 6. And that's not so bad, right? But here's the thing. It can get bad, right? We've done some of these completing the square problems where they get pretty ugly. You guys agree? And then we still have a solving problem to deal with at the end of that. But remember, for completing the square, this was the exact same process every single time, right? So that should mean that if we solve a very general quadratic using completing the square, we can generate a formula that we can just apply every single time. So let's do that. So let's say we have this standard form quadratic. Right? Every quadratic could be written in standard form with some ax squared plus bx plus c, right? And we know how to change them into that form. That's pretty easy, either foiling or expanding. Both of those are easy things to do. Okay? So what I'm going to do is I'm going to do completing the square and then solve this. And the result is going to be a solution for x in terms of A, B, and C. Essentially what I'm going to get is a formula that I can use in order to solve any standard form quadratic without having to go through the completing the square and reverse order of operation solving. It's just going to save me some steps. Okay with that plan? This process that I'm about to do is something that I would never expect you to do on your own. I'm just kind of showing you this so that you understand like where this formula that we're about to generate comes from and how we get it. That it's simply a result of these two procedures that we know how to do combined together in a very general situation. Okay, so we're going to start by completing the square. The first thing we need to do is make sure the leading coefficient is 1. So I'm going to do that by factoring an A out. So there's that. Everybody okay there? Next, I'm going to take this middle coefficient, divide it by 2, and square it. And then I'm going to add and subtract inside that set of parentheses. So b over a divided by 2 is b over 2a. And just for the sake of our notes, I'm going to write it that way so it's a little bit easier for you to see what's going on. Everybody's okay with that? Rather than squaring it also on that step. Okay. The next thing I would want to do is I want to kick those last two values out of my parenthesis. Notice that I just wrote C at the end rather than A times C over A, right? Because A times C over A, the A's are just going to cancel, leaving us with C. So that quadratic part factors. It's going to factor to x plus that middle coefficient divided by 2, quantity squared. Go ahead and do b over 2a squared. So to square a fraction, we square the top, so that becomes b squared. And we square the bottom, which becomes 4a squared. Everybody so far so good? I guess I could put a parenthesis there. So when I do a times b squared over 4a squared, one of those a's is going to cancel, right? Oops, still equals 0. And to add c to the b squared over 4a, I need to make a common denominator. That common denominator would be 4a. So 4a over 4a times c is just 4ac over 4a. I'm now going to move this stuff over to the other side and write it with a common denominator, or write it as a single fraction, I guess I should say. So far, so good. Now I have to get rid of that. I'm starting to solve, by the way, in case you didn't notice, right? We've moved on to solving. The square has been completed. I'm going to get rid of that a coefficient, but since I have fractions on the other side, instead of thinking about it as dividing by a, I'm just going to think about multiplying by 1 over a. So far, so good. Next, we just need to square root both sides. Because we square root both sides of an equation, it creates a plus or minus. And because we're square rooting a fraction, I can think of over the square root of the denominator. Now the numerator can't be simplified anymore because I have a square root of an addition or subtraction problem, right? That was one of the asides we mentioned. But we can simplify the denominator because that's just a multiplication problem. So the square root of 4 is just 2, and the square root of a squared, so our denominator is just 2a. And then I'll subtract the b over 2. Notice that b over a and plus minus square root b squared minus 4ac all over 2a have common denominators. So when I subtract this over, I'm just going to write this as a single fraction because they have a common. Leaving me with this formula. Does anybody recognize this thing?
Oh, no.
This is the quadratic formula. So I've learned this before. So suppose we had this standard form quadratic that we solved before. Remember, to solve this before, we had to do completing the square and then the reverse order of operations, right? But we could now just apply the quadratic formula. So I note that the values for a, b, and c are 1, 2, and negative 5. And then I'm just going to plug them into my formula. So negative b plus or minus the square root of b squared minus ac 2 times a. Two squared is 4. 4 times 1 times negative 5 is negative 20. 4 minus a negative 20 is 24. I noticed that I could simplify the square root of 24 because 24 is just 4 times 6, right? So the square root of 4 is 2. And then I'm going to write these as two sections since they both have the common denominator. So negative 2 over 2 becomes negative 1. And 2 root 6 over 2 just becomes root 6. And there's our same answer that we got before, with I would consider considerably less work. Isn't that nice? Okay, so let's just kind of recap. We can just use the zero product property, always. If we're inverting, we can use the quadratic formula, always. Or sometimes we can factor and then use the zero product property. Or I guess I should probably also say, or sometimes we can think of it as a vertex form and use the reverse order of operations. Why would I want to do anything other than the quadratic formula for a standard form problem? Sometimes these are much, much faster, right? If the factoring you can use a shortcut on, that's going to be faster than grinding through the quadratic formula, right? If it's just like 4x squared minus 10 equals 0, going to be probably faster to just burn through the reverse order of operations and use the quadratic formula. That's the advantage of those ones, is they're fast. But the quadratic formula works every time. And it's really the same amount of work every time, so it's not like it's really bad. But I just thought I'd kind of recap things going on here. Now we still have one problem here that we haven't addressed. Let's look at an example. Oops, that was weird. Actually, let's make this problem simpler. That'll do. Let's just do that. Make it real obvious. What's going to be the easiest way to solve this problem? Yeah, I would just do the reverse order of operations on this, right? Very fast. Subtract 1 from both sides. Square root both sides. So x is equal to plus or minus the square root of negative 1. Does anybody see a problem with that? Well, does anybody see a problem with what I've written? Ella? Yeah, what's the square root of a negative number? So you're telling me there's two numbers that I can, identical numbers that I could multiply together to get negative 1. So there's not two real numbers that do this, right? So this has happened to us a bunch of times before, though, in our mathematics education. Back in elementary school, when we learned subtraction, eventually we got to a problem like 3 minus 4, and we got a result that we didn't have a number for. What did we do? We introduced negative numbers. Later in elementary school, when you started doing division, eventually you got to a problem that you couldn't do division on, like 3 divided by 4. What did you do? Introduce decimals and fractions. In high school, you got to things like you started square rooting things, and you got to things you couldn't take the square root of. What did you do? Like the square root of 2. You added on the rest of the real numbers to include these irrational numbers like the square root of 2 or pi, right? What are we going to do now? We're going to add on more numbers. Exactly right. So this new set of numbers that we're going to deal with are called the complex numbers. So the complex numbers are numbers of the form a plus bi, where a and b are real numbers. I is equal to the square root of negative 1, and I is called the imaginary number. So let's just do a quick couple of examples to decide whether some of these things are complex numbers or not. About 7 minus 3i. Is that a complex number? Is it a plus bi? Yeah. What's the value for A? What's the value for B? Negative 3, right? So yes, it's a complex number. How about 1 plus I? Is that a complex number? Okay. What's the value for A then? And what's the value for B? Okay. What about 3 minus I over 5? Is that a complex number? It is. We can just think about it as 3/5 minus 9. Right? You can just write that as two separate fractions with a common denominator. Is everybody okay with that? How about 7i? Is that a complex number? Sure it is. Can't think about it as 0 plus 7i. What do you think? Still okay? 8. Is that a complex number? Sure it is. Can't I think about it as 8 plus 0i? So what's the takeaway? Everything that we've seen to this point can be represented as a complex number, which is as it should be, right? When we extended the positive whole numbers to include the negatives, we formed the integers. We don't want to kick out the stuff we had before. We needed to add it on, so our new definition included everything we had before, right? Same idea here. When we add on these imaginary parts, we want to make sure we keep all the things that we had before in the same definition. So before we talk about solving with this, we should talk about how we do operations on complex numbers, like add, subtract, multiply, divide value, stuff like that. So here's two complex numbers that we're going to add together. 3 plus 5i plus 7 minus 2i. How would you hope that this works? We'll just add the real parts together and then add the imaginary parts together. And that's it. 3 and 7 made 10. 5i and negative 2i made positive 3i. No big deal, right? Basically, what are we doing here? Just combining like terms. Is that okay? Okay. What's going to be the thing that we have to be careful about in subtraction? Yeah, the subtraction symbol. Why do we have to be careful about it? Yeah, because it distributes to everything in the parentheses, right? So here we should get negative 4. Plus everybody okay there? So again, pretty easy to deal with. What if I have 5 times 3 minus 2i? What do you think we should do here? Yeah, just distribute. What if we have 5i times 3 minus 2i? Still distribute, right? Okay, so what do I get? 5i times 3i is 15i. And 5i times negative 2i is negative 10i. But that's not in the form of a complex number, right? What's wrong with it? We have these I squared in there, right? So if I is equal to the square root of -1, what's I squared going to give us? -1, right? Everybody agree with that? If I square both sides of I equals the square root of -1, the squared cancels the square root, and we're just left with the -1. So this just will turn into a -1. So -10 times -1 is +10, and then still plus 15i. We okay there? All right. What if I have 6 minus 2i times 3 plus I? What do you suppose I should do here? FOIL. Yeah, exactly right. I get 18i. Whoa, minus 6i. Didn't mean for this to happen. That's okay, though. Minus 2i squared. So if I combine like terms, notice that 6i and -6i cancel out. And I squared is the same as -1. So really I have 18 minus 2 times -1, or 20. Am I always going to get a pure real number when I do this? No. More often than not, it'll still be another imaginary, or have an imaginary part. But this is a special situation that we'll look at a little bit more in a second. I didn't mean for it to happen, but it's okay that it did. So far, so good? Again, all of this is run pretty much as we'd hope, right? Very much just like all I have to do is treat the I like you would an X, and everything is fine. You know what I mean? Okay. What are we? Division now, right? Well, we've seen the easiest situation. How do I do 3 plus 2i divided by 4? Yeah, you just write it as two separate fractions. And now you could reduce the 2. But that's not a big deal, right? What if instead it was 4i? Instead of just 4. Can I do the same thing? No. Why won't it work? Because I'll still have i's in the denominator if I try to do the same thing, right? Can a complex number have an I in the denominator? No. So this is the trick. What we'll do is we'll just multiply the top and bottom by I. Why will that work? Because I squared is -1, so we'll have no i's left in the denominator. And then we can do the same thing we did in the previous problem, right? So that distributes. And then we know I squareds are the same as -1s. I can write this as and -2 over -. Are we all okay with that? So still not bad, right? If there's an I in a single I in the denominator like that, just multiply the top and bottom by I and move on about your day. Here's the trickiest situation. What if we have something like 2 plus 3i over 1 minus 5i, where we have a full complex number in the denominator? Can I just multiply the top and bottom by I and take care of it like we did the previous problem? No, because when we distribute the I through the denominator, we still have an I stuck there, right? So what are we going to do? We're going to multiply the top and bottom by 1 plus 5i. These things are called conjugates. A conjugate is where the sign in the middle is different, or is opposite, I should say. But you're just going to use whatever is in the denominator with the opposite sign in the middle. And then we're just going to FOIL this stuff out. Plus 3i plus 15i squared. And then 1 plus 5i minus 5i minus 25i squared. So if I combine my in the numerator, and they just cancel out in the denominator, I know that I squared is the same as negative 1. So in the numerator, I have 2 plus a negative 15, so negative 13. And then I have plus 13i. In the denominator, I have 1 minus 25 times negative 1, so 1 plus 25, or 26. And now it's just like the two separate fractions, and in this case, reduce. We okay there? That's really the worst one. Or the worst situation of all of these, right? But it's not so bad. You just have to do a little bit of foiling. And yeah, it's all right. It's all right. Okay, so far? We have one more thing to talk about. That's the absolute value. And then we'll be ready to tie this back on to solving. So an absolute value is measuring, like, if we think back to our normal definition, is measuring the distance from that number to 0 on the number line, right? Everybody's okay with that? Okay, so if I give you the complex numbers here, 3 plus 2i and 2 plus 3i, which one would come first on the number line? Doesn't make sense, does it? Good, it's not supposed to. So you can't compare a complex number to another complex number with a less than or greater than operation, because there's two components to it. So we're not going to be able to put these on a number line. What we can do is we can graph them in like a two-dimensional space. So if I do 3 plus 2i, we can put the real part on the x-axis and the imaginary part on the y-axis. And so I go like 3 over and 2 up. If I wanted to do 2 plus 3, okay with that. So instead of a number line, because there's two components to it, I need a plane. Everybody's okay with that notion? What represents 0 on a plane? The origin. So the absolute value is going to be the distance from that location to the origin. Well, one way I could find that is if I think about this as a right triangle. I went 3 to the right and 2 up. So how do I find that third side? Geometry. Starts with a P. So one thing from geometry you should have never forget. That's it. So if to consolidate this then, I have a complex number. It's just the square root of a squared plus b squared. Because in this case, it's just like the hypotenuse of that right triangle, right? So it's just the Pythagorean theorem. Is everybody okay with that? Say we have 3 minus 4, or the absolute value of 3 minus 4i. So that's just fine. Is that okay? So again, really simple, right? You just plug it into the formula, and out comes your answer. Will it always be a whole number like that? No. But it'll always be a real number because it's a distance. Okay. So now, let's go back to solving. Because now we have the final ingredient that makes every quadratic equation solvable for us. So let's say we have x squared plus 2x plus 5 equals 0. How would you want to solve this? It's in standard form. Is it factorable? You take a quick look and you can probably say no, right? There's not two numbers that multiply to give you 5 and add to give you 2. So if it's not factorable, and it's in standard form and not easily writable in vertex form, how should we solve it? The quadratic formula. Square root of b squared minus 4ac all over 2 times a. So we have 2 squared, which is 4, minus 4 times 1 times 5, which is 20. 4 minus 20 is negative 16. So we have a negative under our square root, right? That did present a problem to us, but no longer. Just remember that negative 16 is the same thing as 16 times negative 1, right? So the square root of negative 16 is the square root of negative 1 times the square root of 16, or I times 4. Okay with that? I typically write it as 4i, but if you wrote I4, I guess I wouldn't mind. But don't do that. And now I can just write this as 2 separate fractions and reduce. So negative 1 plus or minus 2i. And that's it. Any questions from this? Okay, thanks. We'll stop here. You guys did a great job.